All right, guys. So today we're going to cover two theorems, and they're honestly both pretty easy. The only thing that's a little bit annoying is that when you're tested on theorems for the calc test, you have to a little bit follow a script. So you're going to get a set of study sheets, okay, that we're going to accumulate throughout the semester that you're going to get to use on the semester exam. Okay, so this top page, not the whole packet, is your second paper that goes in that set. So go ahead and disconnect it from the packet. Okay, the first sheet is the one you got on the last test day. So you're going to want to try to keep like these special papers together. So your test one cheat sheet, that's a special. Okay, this top sheet, this is also a special that you'll be able to use on tests all the way through the semester. Okay? All right, so the first thing that we're going to cover, we're only doing two theorems today. Okay, the first one is intermediate value theorem. So let me explain to you what it is. Okay, we're going to draw a little picture here. Okay, so let's read through it. It says a function f is continuous. So I want you to start off by drawing a continuous function. So let's just make it look like, bless you, make it look like that. So this is my f of x. So far, we're following instructions. It's continuous. Then it says for any number k between f of a and f of b. So let's pick an a and a b. So I'm going to let my a be here. Then f of a would be how tall that is, or the y value at that spot. So this is f of a. And then let's place our b just a little bit further down the line. So let's maybe put b over here. Then that means that f of b would be that y value, which is right there. Now, where does it say that k has to be in relation to f of a and f of b? It says it has to be what? Where does it say it has to be, though, between f of a and f of b? It says it has to be between them. Very good. So I want you to pick a k at a height that's between where you place the f of a and the f of b. So I'm going to say that my k value is here. Okay, but it has to be between the f of a height and the f of b height. Okay, then here's what it says. For whatever k value you picked, as long as it's between f of a and f of b, there has to be an x value, we're going to call it c, so that f of c is equal to that k. So here's basically what that means. Probably that doesn't really make sense when I just read it. Okay, that if I pick a number between the starting y value and the ending y value, there has to be a spot where that y value that I picked has an x value that goes with it. So in this case, my k value is here. Well, then I know that my value that it happens at is right here. So you're basically promising that for any y value between the beginning and the ending point, okay, I know that it had to happen somewhere along that interval. So this would be my x equals c. And then for that k value, okay, f of c would equal that number. Okay, so let's give ourselves some little steps to follow. So step number one is that this theorem only applies if your graph is continuous. Okay, if it's not continuous, then you can't use this theorem. So that's step number one. Step number two is that the y equals k value that you want has to be between f of a and f of b. And then remember, f of a and f of b, those are the y values at those x's. Okay, if those two things are true, that your graph is continuous and that the K value that you want has to be between f of A and f of B, then intermediate value theorem promises that there's an X that goes with that Y. So let's write that out. Therefore, IVT, that's intermediate value theorem, okay, guarantees that there is an X so that f of C is equal to that special K value. So IVT promises that there's going to be some X that goes with that Y. Okay, so when you're ready, go ahead and take a look at your packet with all the different questions on it. Okay, we're not going to do every single one. We're just going to do a couple of each type to make sure you kind of have the idea. Are we ready to go? Everybody good? All right, so take a look at number 1. Now, I just pulled this chart off of Google. So it's supposed to be the height of a child, okay? But this is obviously a growth curve for like all children. So let's pick one height. Let's pick the one that's dead center. So this is the baby that we're talking about right here. Okay, obviously there are other lines, but we just have to pick one to use for our example. So let's read the question and we'll do it. So it says, suppose the height of a child is a function of age shown on the chart below. Does intermediate value theorem guarantee that the child must have been 90 centimeters tall between 2 and 4 years old? So follow your structure. Number 1, f has to be what kind of function? Starts with a C. Continuous, very good. So number 1, you're going to think about whether height changes continuously. Okay, that is a yes. Remember, continuous just means connected. So you don't go to bed 5'8", and then all of a sudden, in an instant, you're 5'10". Okay, you slowly grow over time or maybe shrink over time when you get really old. Okay, but it is a continuous function. So we're going to put here that height is a continuous function. Okay, step number 2 is that I have to check that the height that I want is between the beginning and ending heights of my time interval. So for step number 2, normally you wouldn't write this, but since it's your notes, I'm going to put what you're doing. Check that we specifically want 90 centimeters is between the child's height at 2 years old and 4 years old. And then this is where the chart is going to come in. So to abbreviate height, we're just going to call it H. So let's find H of 2 and H of 4. And we're going to pull those values off of the middle line on that little growth curve. So 2 years old is right here. Approximately, how tall is the child at 2 years old? Just give me an estimate. This is 70, 75, this is 80. So that would be about what? 77 is great. So we'll say he's 77 centimeters tall when he's 2. Okay, then how tall is he at 4? Another just approximation here. He's not quite 95, so maybe he's 93, 94, sure. Okay, so 90 centimeters is the Y value that I want. Does it fall between these two Y values? Yes or no?
Yes.
Yes? Then I know that he had to hit 90 centimeters before he could grow to 90. So I'm going to put here that 90 centimeters is between, we're answering that question, 77 and 93. Therefore, IVT guarantees a moment where child's height was exactly 90 centimeters. But remember, if this is a continuous function, okay, like height is, then that should make sense. You can't go from 77 to 93 without hitting all the heights between them along the way. Okay? All right, take a look at number 2. So it says the table shows the weight of an adolescent child, okay, measured in pounds as a function of time measured in years of age. Part A, does IVT guarantee the child must have weighed 40 pounds between 3 and 5 years old? So the first thing that you're going to check is whether or not weight is a continuous function. Now, we're going to pretend yes. Okay, if you had your arm chopped off, then automatically you could, I guess, technically lose like 10 pounds in an instant. Okay, but we're going to just say in general, okay, weight is continuous. Okay, so little check there. The second thing I have to check is that the weight that I want has to be between the weights at the beginning and end of my time interval. So what is the weight that we want the child to have? Exactly 40. So I'm going to check that 40 pounds is between the weight at what time periods? 3 years and 5 years. Okay, and then we're just going to use our little table for this. So write down the weight at 3 and the weight at 5. So weight at 3 is 35 pounds. The weight at 5 is how many pounds? Read it in your chart. 42. Then is 40 between those? Yes. Then can I promise the baby hit 40 pounds for some period of time within that interval? Yes. So we would put here 40 is between 35 and 42. Therefore, IVT guarantees a moment or a day.
Please pardon this interruption. Teachers, at this time, if you will please release freshman volleyball to go to the locker room. Thank you.
Okay, IVT guarantees a moment where the weight is exactly 40. Okay. Now, the one thing about this theorem that's like kind of makes it a little silly is that this doesn't necessarily help you find what day it would happen. It pretty much just only tells you that it would happen, but it doesn't actually say like, oh, it would have been on this day. Okay. For part B, we want to know if we can promise the kid would hit 9 pounds between 0 and 1. What is the baby's weight at 0? Okay, 10 pounds. And what's the baby's weight at 1? 25. And we want the baby to hit what weight for part B? 9. Is 9 between those? Then you cannot promise that the baby's weight would hit that number because it only applies to intermediate values, meaning between the endpoints. So we would put here that 9 is not between 10 and 25. Therefore, IVT cannot guarantee a moment when weight is 9 pounds. Okay, but you're just going to follow that exact same structure when you're doing this. Now, let's talk about realistically here. Okay, if the baby was born at 10 pounds, and it grew to 25 pounds. Okay, you may not know a lot about babies, but a lot of times they do lose weight right after they're born. So is it possible, this is now part C, that the baby's weight dropped to 9 pounds? Is that possible? Sure, but IVT just can't promise that it happened. So for part C, where it says, is it possible? You would say, yes, it is possible, but not guaranteed. I'm going to put possible, but not promised. Okay, and the reason it's not promised is because 9 is not an intermediate or between value for the 10 and the 25. Okay? So down there at the bottom, it says, this theorem can only guarantee that it does happen. It can't promise you that it doesn't happen. It can only promise that it does or maybe, but it can't tell you for sure that it didn't. Okay? All right, one more example with a table like that. Go ahead and turn to number 3. Next one says, suppose the value of your bank account is given in the table to the right for certain days in September. Does IVT guarantee that your bank account was 400 for some day between September 1 and September 10? How much was in the account September 1? 300. What about September 10? 500. And how much do I want? 400. Is that between those? Yes. But think about your bank account. Does it steadily grow 1 cent at a time? No. You put in a deposit and it just jumps $50, right? So your bank account is not a continuous function that I can't promise this. So your first condition is it has to be a continuous quantity. So for our step 1, we're going to put that our bank value is not continuous. It can jump $100 in an instant if you make a deposit. And if it's not a continuous function, then even if the number I want is between the endpoints, I can't promise you my bank hit that exact amount. So we'll put therefore, IVT cannot promise that the account hit exactly 400. Okay, so IVT cannot guarantee that it would hit 400 because it's not the right type of equation. It only applies for continuous functions. Now read part B. It says, is it possible that you made an exact $100 deposit and that it hit exactly 400? Okay, yes. It's possible, but not promised. So remember, IVT can't eliminate the possibility that something didn't happen, but it can promise that something did happen if the conditions are met. Okay? All right, come down for me, please, to number 4. Okay, so we did a couple with a graph, with a table. Now we're going to do one with an equation. Okay, first question is, for the function f of x equal to x cubed plus 1, is that a continuous graph? Just think about the shape. X cubed plus 1, I'll give you a little picture in case you don't remember. Cubics are like the little squiggle, and the plus 1 would shift it up 1. So I'm going to go up 1 right here, and then I'm just going to draw what that graph would look like. So thinking about the shape of that graph, is it continuous and connected all the way through? Yeah. So we'll put f of x is continuous. Okay, and I'm going to put a little check. That we thought about the graph, yes, it's continuous, moving on to step 2. Okay, we are now looking for what y value they're wanting us to prove happens. So we want to guarantee that f of x has a root on the interval. If you don't remember what a root is, okay, a root is the same as an x-intercept or a 0. Okay, so x-intercepts are sometimes called roots. So if I want to prove that a root happens, what y value do I want to prove that my graph has to hit? I need it to hit 0. That's what an x-intercept is. So I need to check that 0 is between my endpoints. So rather than writing that little sentence, we're just going to do it. We're gonna find the endpoint at -2. We're gonna find the endpoint at 2. And then we're gonna check that 0 has to be between them. Okay, but since I have an equation, instead of me just pulling them off the graph, I'll have to actually find them. So we'll do -2 cubed plus 1. And then this one will be regular 2 cubed plus 1. -2 times -2 times -2 would be -8. And -8 plus 1 is -7. So my starting y value is -7. Now let's do it for +2. 2 times 2 times 2 is how many? 8, and 8 plus 1 is 9. And what's the y value that I need to prove happened? What number? 0. Is 0 between those? Then I know it has to happen. So let's say your -7 is here, your 9 is up here, then I know that I would have to hit 0. So let's write that out. 0, which is the k value that we want, is between -7 and 9. Therefore, IVT guarantees an x equals c, so that f of c equals that number. Okay, write that down, see if that makes sense. Okay, I know there has to be an x value where at that x value, my answer is 0. Okay. All right, let's do one more like that. Take a look at number 5. This time we're doing x squared. Think about the shape. Do you remember the shape of x squared? Shaped like a U, very good. So think about if it's a U shape, is it connected all the way through? Yeah. So we know that f of x is continuous. And pretty much any power function like x3, x2, x4, they're all going to be continuous. Okay, the second thing I need to check is that the y value that I want, which in this case again is a root, we know that's 0 now, has to be between the y values of the endpoints. So my interval is -2 to 2. So I'm going to find f of -2 and f of +2. So I want to find my y value at the beginning of my interval and then my y value at the end. My equation is just take the x and square it. So what is -2 squared? 4. What about regular 2 squared? 4. And I want 0. Is 0 between those? No, nothing can be between 4 and then 4 again. So I would say 0 is not between 4 and 4. Therefore, IVT cannot promise an x equals c where f of c is 0. Okay, I can't promise that there's a root because 0 doesn't fit between the y values at the beginning and the end of the interval. Now, could there be a 0? Yes. And if you look at the graph that we drew, does it actually touch 0? Yeah, it touches it right here. Okay, but remember, IVT doesn't promise it doesn't happen. It just says it doesn't have to, right? So I can't use this theorem to prove that it hits 0. All right, y'all are doing great. Let's skip 6 and 7. Let's jump down to number 8. Okay, just to shorten these up a bit. That's okay. Your notes are there on that back table. All right, we're gonna skip 6 and 7. We're going to number 8. Okay, so my equation is sine x. Okay, you should have graphed sine and cosine graphs for like a whole month in pre-cal. So if you don't remember the shape, it's a little wavy guy and it starts at 0. So you're gonna go uphill, downhill, uphill, downhill, uphill, downhill forever. And then the other way, you're gonna do the same thing. Okay, so that's what your graph looks like. Now, the 4 would make the wave a little bit taller, but we don't care about that. We're not going back to pre-cal. So first question, continuous or not?
Yeah.
Yes, f of x is continuous. Do a little check mark. Okay, we checked the graph. It is continuous. Then what do I find next? I find my y value at the beginning and the end of the interval to see if the y value that I want is between. So let's do it for pi 6 first. And then we'll check pi halves second. Okay, now for your hand trig, I accidentally erased the board that had the fingers on it. But pi 6 is your ring finger. So we want to know what 4 sine pi 6 is. Well, then bend down your ring finger. Remember, sin is down. So you're counting the fingers below. Below my ring finger, I only have one finger. Square root it. What's the square root of 1? 1. Put it over 2. It's 1/2. So it's 4 times a half. And half of 4 is 2. So my starting y value for my interval is 2. Now let's do it for positive a half. Which finger is pi halves? You remember? It is the thumb. Very good. Sin is down. How many fingers are below your thumb? 4. Square root it. What's the square root of 4? Square root of 4 is square root of 4 is 2. And then 2 over 2 is 1. So it's going to be 4 sine pi halves. We said that sine of pi halves is 1. And then 1 times 4 makes your ending y value. Okay, remember that the y value that I want, we call it the k value. We want, is it between them or no?
Yes.
Yes, because I start at 2, I end at 4. I can't have any skips because I know my graph is connected. That means that 3 has to happen. So you would say 3 is between 2 and 4. Therefore, IVT guarantees an x value so that f of c is 3. Again, we're not having to find it. We just know that there is one. Okay, do you kind of get the idea here? All right, go ahead and turn the page. We're just going to do one off the next page. So on the next page, you have a table. Okay, you don't know what f and g look like, but it has to state in the question that your functions are continuous. Okay, now if you look at the top here, it does say that they're continuous. Okay, but that has to be true for you to be able to do it. Okay? So let's do part B. Okay? So we want to prove on the interval from 2 to 3, so these are the x values, that my graph is going to equal 5. This is the k value, which remember is a y value. And it's the specific y value that has to be between the y values that I have. Okay, so first thing that I'm going to check is that f and g are continuous. We already boxed that they are. So I'm just going to put number 1, f and g, continuous, check. Okay, not a real sentence, but you kind of get the idea. Step number 2 is I need to find the beginning and ending y values for the function that I was given. Now, I want you to notice they're not asking me about f or g. They're asking me about the product of f and g. F of x times g of x. That's what that notation means. So if it's f dot g like that, that means I'm going to multiply f and g's answers together. So first let's do it for 2. Then we're going to do it for 3. And then we're going to see if 5 is between them. Okay? So do f dot g of 2. and then f dot g of 3. Now, I will say I kind of hate this notation, so I'm going to write it like this because I think you'll remember what it means better if you look back at these. Okay, but that notation where you put just the dot between the f and the g, that actually is a real thing. Okay, but these are the same. You're basically giving them each their own 2 and then giving them each their own 3 and then multiplying in the middle. So in your chart, find 2. What is in the F column for 2? 4. And then what's in the G column for 2? So that'd be 4 times 0. 4 times 0 is 0. Okay, now we're doing the same thing for 3. Find 3. At 0, what's my y value for F? 0. My y value for G is 0 times 2 is 0. My number that I want to prove, 5, is supposed to be between those, is it? No, then I can't prove that the graph would hit 5. So you would say 5 is not between 0 and itself. Therefore, IVT cannot guarantee. And I'm just going to leave it there because we've probably broken your hand enough. Okay, guarantee this. So we're just going to kind of shorten it up. Okay, any questions on intermediate value theorem? Okay, the other theorem is pretty easy. So go ahead and go back to your cheat sheet. Okay, remember, we're not going to lose this paper. We're going to keep it with the cheat sheet from test number 1 so that all the way through the semester exam, you have a couple pages to study that you get to use on the exam. Okay? All right, squeeze theorem. Okay, draw me a little graph. Okay, we are going to do 3 functions, f, g, and h, and they have to all be continuous. So I'm going to draw, and let's do h of x here. And then I want you to draw a g of x, but I want you to let it touch h of x somewhere on the graph. So I'm going to let it touch like that. Okay, this is g of x. Okay, now I want you to read the inequality. So they all have to be continuous. And then what it says right here is that my f function has to always be between g and h. Do you see that right here? So I want you to draw your f so that it's sandwiched between the 2 functions that you just drew. So I'm going to draw my f here, and then it's going to get pinched and keep going. That's f of x. So here's essentially what the squeeze theorem says. Okay, that if you have a function f that has to stay between 2 other functions, and those functions touch or equal each other, like they do right here, okay, then your f would have to also hit that same number, because that's the only way that it could stay between them. Now, we're using the word between a little bit loosely because do you see on these equal to's that means it doesn't have to be between, it could be equal, right? Okay, but if your functions squeeze together, then f has to equal the same thing. Okay, so let's write out your steps. Okay, first step is that they have to all be continuous. So f, g, h, all continuous, and it has to say that. Okay, or it could tell you what the equations are, and you could kind of think about the picture like we did. Okay, but they have to all be continuous. Step number 2 is that it has to state that f is always between g and h. And those are the 2 things that we circled. So they're all continuous and f stays in the middle. Okay, step number 3 is that g and h have to equal each other at the same value. So g and h have the same limit value equal to L. They have to touch, they have to intersect and have the exact same limit value, or we'll even put maybe Y value here. You like that better? Because we know that on the graph, the limit is a Y value anyways. Okay, if those conditions are met, then you automatically know that the limit for F has to equal the same number. Okay, the limit for F would have to equal that same L as the other two. Okay? So go ahead and turn to the last page of your examples. We're just going to hit 2 of these. Okay, we'll start with number 11. Okay, first condition is that it has to be continuous for all of your functions. Okay, so think about the shapes that they're giving you for 11. Okay, x squared is a parabola that looks like this. Would that be continuous? Connected all the way through? It's like a negative x squared, a U graph? Sure. Okay, negative 8x plus 2, that's a line. Okay, specifically it would be a downhill line. Okay, but are both of those continuous? Yes. So step number 1 is that you would want to check that F, G, and H are continuous. Okay, we thought about the graphs, we checked it out, everything's good there. Step number 2 is that you have to know that F stays between them. Now, does it say that in question 11? Right here. Okay, they give you the inequality. Okay, so I'm just going to put F is between G and H. Okay, and that has to be true for you to use this theorem. Okay, the third statement is that you need to make sure that the Y values at the limit you want are exactly the same. So I want the limit for X approach 4. Then I'm going to find G of 4 and H of 4 and see if they come out the same. If they equal each other, then they're going to squeeze F to have to equal that same number too. So let's plug into H first just because it looks easier. So it's negative 8 times X, which is 4 plus 2. Negative 8 times 4 is what? Negative 32 plus 2 is negative 30. So I know that H hits negative 30 for the Y value. Okay, now let's see what G hits. So I'm plugging in a 4 to this equation right here. So it'd be negative 4 squared minus 5 times 4 plus 6. 4 squared is 16, then turn it negative. 5 times 4 is 20. Negative 16 and negative 20, that'd be negative 36, plus 6 back would be negative 30. Okay, so if G hits negative 30, and H hits negative 30, and F stays in the middle, then what does F have to also equal? Negative 30. Answer choice B. Okay? All right, last one we're going to do is number 12. Okay, first question. Think about sine X and cosine X. Are they both continuous? They're both little waves, right? So we know that they're both continuous. So for number 1, I'm just going to put a check and be really lazy. Okay, number 2, they have to state that F is in the middle, do they? Yes, check. Step number 3 is we need to find the Y values and make sure that they equal each other so that they squeeze F to that same value. So the X that I'm approaching is what number? Pi thirds. So we'll find G of pi over 3. We'll find H of pi over 3. And if they meet, then I know my F is the same. So let's do 10 sine X first. So that'd be 10 sine pi thirds. Find your pi thirds finger. Pi-thirds is your pointer. Sin is down. So you're picking your down fingers. How many? √3. And then remember, you always put it over 2 for the formula. Then we're going to times that by 10. Now, in pre-cal, you should have learned that if there's a 10 and a divide by 2, you can do that. So 10 divided by 2 is 5 square root 3. That's my first y value. So if my second one comes out the same, then I know my limit for f. Let's do it. My second equation is 2 cosine x plus 2. Well, then it's 2 cosine pi thirds plus 2. Fold your pi thirds finger down. Still your pointer. Okay, remember cosine's your top. You only have 1. Square root of 1 is still 1. Put it over 2. Means that it's 1/2. And then remember, I'm going to take half of the 2 that was in front of it. What's half of 2? 1, and 1 plus 2 makes 3. So did they come out the same? No, and if they're not the same, then you can't tell me what f equals. So you would pick the answer choice that got hole punched. Okay, there's not enough information to determine. Okay, these have to be the same for you to use squeeze through. Okay? All right, so pull out your Chromebooks. We're going to do one of the IVT questions together just to kind of make sure that you understand where to like fill in the blanks with what, and then y'all have the rest of class to work. Okay, your homework today shouldn't take very long because you're just looking mostly at graphs. Okay? So pull out your Chromebooks. Yeah, Rodrigo is on the struggle bus there for a minute. Music. It should be a 5. Uh-huh. Yeah. You got a question? It should be a 5. And then this one should be a 4. Huh? All right, let me show you how this works. Okay, first thing that you're gonna do is it has to tell you it's continuous. Now, here's why. When you look at the graph, do you see all the question marks? It's like, ooh, it's a mystery. What happens in there? Okay, so they have to tell you it's continuous. Do you see that in the problem? Does it say it's continuous? Yes, then go ahead and click. Since the function is continuous, then IVT can be applied. Now, it can only be applied, let me move this out of the way. Okay, it can only be applied if certain conditions are true. So as soon as you hit that you can use it, a bunch more boxes pull up. Okay, it says for any value k on the interval, now this is important, k is a y value. So what are the y values where the graph cuts off? My first y value is 2, because we're listing how high or how low it is. And my ending y value is 5. Do you see that? So my k has to be between 2 and 5 for my height. Okay, then it says there exists a c. Remember, c is an x value. So where are the x's for the interval between -2 and 3? Now, if you want like a little cute way to remember it, okay, it's kind of stupid, but just pretend. Okay, you would be like, okay, why would I ever want to see my x? Okay, why would I ever want to see my x? Okay, hopefully you don't want to see your x. Okay, but k and y, k is a y value, has to be between the y's. And then c is an x value, has to be between the x's. All right, now last little bit of this. So it says, okay, what about 0? So if f of c is supposed to equal 0, is 0 between the k's not the x's, the k's, which are y values, because ky, whatever, I want to see my x. So is 0 between those? Between 2 and 5 specifically? No. Then you would say there may not exist a spot where that happens. Why? Because 0's not between the y values that the graph ends at and then restarts at. It's not between. Okay? Now, you're never going to click there does not exist. Because remember, it can't promise you it didn't happen. It can just promise you if it did, or maybe it did and we just don't know. Okay? And then I hope that kind of helps there. One more thing I want to say before I let you work. If these y values were backwards, let's say that it started at 5 and then it dropped back to 2, you would still have to list these smallest to biggest. So even if the 5 was at front and the 2 is at the back, you would list it small to big, okay, for the y values for the k. All right? Yes. Yeah. But remember, it has to tell you it's continuous or you're clicking no. It should be 2 to 5. Did I count something wrong? Is he counting it right for y'all? 1, 2, 3, 4, 5. -2 to 3. Yeah, I counted it right for me. It is continuous, it ends with 5. Oh, you're on question 1. We did question 2. That's okay. Yes. So it never said it's continuous. Click not necessarily continuous. Because remember, you don't know. It doesn't tell you it is. So it might be continuous, but we should not. When you cannot apply it if it's not necessary. So there may not exist. Correct. C should be between the x's, -4 and perfect. Good job. Yeah.